This example is provided for the illustration of the generalized principle of inclusion and exclusion. It is available on a book of Chong and Meng on the principles and techniques in combinatorics. This is to illustrate again the generalized principle of inclusion and exclusion as to how do we identify the results if we are going to have here let S be 1 to 14. These are the elements here. These are the elements. And let P sub 1, P sub 2, P sub 3, and P sub 4 be 4 given properties. We are going to assume that an element in J, element in S, whatever would it be, possess a property P sub I if in the grid of I sub I and J, it's indicated by a check mark. Hence, say for example, this check mark here indicates that element 6 has a property of P sub 2, and so on and so forth. So our goal here is to identify the use of the omega for each of the corresponding property, and later on this applicability on the generalized principle of inclusion and exclusion. We would be checking the generalized theorem in order for us to really show that it's true. Now, let us say, for example, we're talking about the omega of P sub 1. This would mean we're going to count the number of individuals, or in this case elements in the set S, having the property of P sub 1. So simply look into the grids. You have here 1, 2, 3, 4, 5. 5 of the elements possess the property P sub 1. So we have here the omega of P sub 1 is 5. So simply count it. Okay? Next, the omega of P sub 2. You will have here the number of elements that comprises or possess rather P sub 2 characteristic. So you have here 1, 2, 3, 4, 5, 6, 7, 8, and 9. There are 9 of them which possesses our characteristic P sub 2. So we have here 9. For our omega P sub 3 and omega P sub 4, again that's omega not W. So similar thing, we count for P sub 3, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, and then 6 as well. Both P sub 3 and P sub 4 characteristics has number of elements 6 possessing them. Okay. Now, of course, we're going to talk about the generalized, generalized theorem for the principle. So actually, it's defined in this manner: the E of your M. Okay, so how many M's, how many elements are there which possess the M characteristics? We have here the omega sub M plus, we have the, that's minus M plus 1 combination M times omega of M plus 1. Then you have here plus, you have M plus 2 M, the combination, omega of M plus 2. I guess we'll end up until omega sub 4 because there are only 4 possibilities here. That is actually for whether all of the elements possesses all properties. So you have 4. Okay, so let's have it later. So let's continue with this one here, the expansion of this formula. Plus, that's minus, alternating minus, you have M plus 3 combination M, and you have here omega of M plus 3, and you have here, because we may start at 0, right, but M is 0, so you have here plus M plus 4 combination 4 omega of M plus 4. Okay, hence we just have first this result if we have the omegas for 1, but we have M plus 1, M plus 2, M plus 4 here, so we need the rest. So let's look at the next possibilities for our pairs. Let me have it here, the omega of P sub 1 and P sub 2. So how many elements possesses P sub 1 and P sub 2 characteristics? So both of them, 1 should be both, 2, 3. There are 3 of them. It should be both of them. Okay, so there is actually 3. Omega of P sub 1 and P sub 4, P sub 3 rather, P sub 1 and P sub 3, 1, it should be P sub 1 and P sub 3, 2, right? 3. Okay, so there are 3 of them possessing 1 and 3. Next, for P sub 1, and P sub 4. Sorry. Take out the combination. It doesn't matter if they're interchanged. So for 1 and 4, you have 1. Should be 1 and 4, right? In this area, 1 and 4. 2. Only 2. Okay? So there are 2 of them. 2. Next would be for the combination of P sub 2 and P sub 3. So 2 and 3. Again, look at this one here. So you have 1, 2, 3, 4. There are 4 of them which possesses P sub 2 and P sub 3. So you have 4. Next, P sub 2, P sub 4. 2 and 4. Look into this. So 1, 2, 3, 4, 5. There are 5 of them which possesses P sub 2 and P sub 4. And finally, for P sub 3 and P sub 4. So P sub 3 and P sub 4, look into this. 1, 2, 3, 4, 5 as well. There are 5 of them. Okay? So 5. So there are 5 of them. Okay. Now how about groups of 3? I don't know if I could copy that one, but let's look into that later. So you have here, to change the color. So you have here P sub 1, P sub 2, P sub 3. Let me actually paste here the same. But it seems like I can't crop that, so I'm just going to move it here at the bottom, so we will be guided with the table as we move forward. So let me increase this, increase further, but only the table will be presented here until 14. There's a pardon for that. Alright, so let me continue. For P sub 1, 2, and 3, it should be the 3 of them. 1, 2. Only 2 possesses 2 elements possess the same characteristic, so you have here 2. So for P sub 1, the next combination 2 and 4, so it would be 1, 2, and 4. So still 1, so 2, 1, 2, only 2 again. So we'll have here 2. The next combination for P sub 1, P sub 3, P sub 4. So let's look into this. 1, 3, and 4. So you have 1, 2, 1, 3, and 4. So again, we only have 2 of them. Then next we have the omega for P sub 2, P sub 3, and P sub 4. Okay? So let's look at this. 1, 2, 3, 4. There are 4 of them. So we'll have 4 here. And finally, for the omega of the combination of all, meaning elements having all the 4 characteristics. So we'll have here 1, 2. There are 2 of them. Okay? So there are 2. Now we have all of this now. So we can actually plot this in our formula. Let me move this. Sorry for that. I'm going to remove that. If we're going to combine, okay, let's talk about omega of 1. That would mean we're talking about all the sum, okay, of this denotation. Previously, when we talked about the illustration of omega sub m, the summation of your, what do you call this one, omega of P sub I. That would mean you simply count those or add those with one element, 5 plus 9 plus 6 plus 6. So we have this one here, this one. So we're asked about omega of 1. So we have the result, which is equal to, equal to 26. Okay. Now, for omega of 2, again, we can simply count or add the results for omegas of P sub, I sub 1, and P of I sub 2. That was the notation before. So simply count or add those results. 3, 3, 2, 4, 5, 5. So 3 plus 3 plus 2 plus 4 plus 5 plus 5, which gives us 22. For our omega of 3, so again, the summation of all omegas with P sub I sub 1, P sub I sub 2, P sub I sub 3, or in short, we're going to add all of this. So you have 2 plus 2 plus 2 plus 4, we will get 10. And for your omega of 4, so this is just equal to 2 as indicated here. Okay? So with all of this already given, let us now look into, but take note, some of these elements. For example, let's talk about element of 3, right? it was counted on the group having p sub 2, right? It's also counted in the group with characteristics p sub 3. It's also counted in the groups having p sub 4. Even counted with p sub 2 and p sub 3, p sub 2 and p sub 4, p sub 3 and p sub 4, and even counted with all the three of them, right? So that would mean there are multiples now. That's why we are trying to include or exclude something. Hence, this is where the generalized principle, after allowing us to identify all of this, if we're going to ask now, how many elements are there, okay, are belonging to a set given exactly one characteristic. Exactly one. This exactly one here, or this, I mean, not exactly one, these ones here were not exactly one, because then again, they are counted in different aspects as well. So that is why we're going to apply the formula of our generalized forms we have here. Let's have omega, this is our generalized formula. Okay, so let me write here, omega of 1. Sorry for that, because I don't, if I'm going to copy this, this is actually in white, so it would not appear in this portion here. And you have here, so let me try to write this as a whole. Okay, so m minus again m plus 1 combination m. You have what do you call this one, omega of m plus 1. Then if you have here plus alternating m plus 2, m omega of m plus 2, minus again, minus m plus 3, m omega of m plus 3, plus, let's just end up here until 4. I believe this is already okay. If it's not, then we can continue with the pattern of the formula, m plus 4. So we are asked, if we are asked about how many elements given exactly one element. So by substitution, you have here omega of 1, which is already given. Okay, then you will have here 1 plus 1 taken 1, omega of 2, plus 1 plus 2 taken, your m is still 1, omega of 3. Okay, that's m plus 1, right? Then you have here minus 1 plus 3 taken 1, and omega of 4. I believe we ended up until 4, right? Omega of 4. So we don't actually need this, by the way, this portion of the formula, just to solve for the exactly one. But we might be able to use that in other aspects. Okay? So if it's exactly 1, our result would be 26 minus 2 taken 1 is just equal to 2 times, for omega of 2, 22, plus 3 taken 1 is 3. Then you have here times 10, that's your value here, minus 4 taken 1 is also 4 times this value 2. So if we just ask about how many of those exactly having one elements, so you will have here the result, 26, sorry, let's place here, 26 minus 44 plus 30 minus 8. That's right, 26 minus 44 plus 30 minus 8. You actually have 4. Only 4 elements having exactly 1. Let's try to check on our table. Okay? So how many of these elements having exactly one property? You have here 2. They only have one property, 6. Only have one property, 12. Only have one property, 13. So I verify that there are 4, exactly 4, having one of those properties. Now this is very clear for this example because we have the table for that, right? But if we have situations not with the table, so we simply need to use the formula. Now, what if I'm going to ask you how many of them doesn't have any elements? Doesn't have any properties. When looking at the table, there's only 2, right? Okay, there's only 2. What if there is no element? I'm talking about, no property. Sorry, element with no property. So I'm going to make this different. I'm going to have here 0, right? Or I'm gonna use the white one, 0. So we have the omega of 0. This would become, the next item here again is exactly no properties. None of those, sorry. None of the properties. none of the properties. So in short, E of 0, sorry. And you will have here 0 plus 1, taking 0. So this is now 0 plus 1. So you can try here 1. So the next one is 0 plus 2. Then you have here your omega becomes 0 plus 2 is 2. Then here you'll be subtracting that 0 plus 3. So this is now omega of 3. And then you have here 0 plus 4. And yes, this time the omega of 4 can be used because we started with 0. Now, take note, in the previous discussion, when you have something like this, it's just equal to n. And that's just equal to n. So this is actually equal to your n. How many are they? 14. Okay, 14 minus 0. 1 taken 0 is actually equal to 1, right? You can try in your calculator. 1 combination 0 is 1 times omega of 1, which is 26. Then plus 2, same thing, 2 combination 0 is equal to 1. And then you will have here omega of 2 is 22. And then you have minus, this is still 1, 3 combination 0 is still 1, times, you will have omega of 3, which is 10. And then you have here plus 4 combination 0 is still 1, omega, sorry, this is omega of 4, my bad. Omega of 4 is this one here, 2. So you have here, sorry for that, 2. So this would become equal to, sorry, I don't have much space. I hope this is still okay with you. So you have 14 minus 26 plus 22 minus 10 plus 2. Let's try. 14 minus 26 plus 22 minus 10 plus 2. Your answer is 2. And it really corresponds to this. Exactly, 2 of them are not having any of those 4 properties. So basically, this is the formula in solving for using generalized principle of inclusion and exclusion. We need to get the omegas per properties, and then you're going to add them to get the corresponding for m properties, and then you apply this formula as you will decide how many are your target, what is your m. By the way, if you can see here before we end this video, if we're talking about 0, since all of the multipliers here are 1, so we can have a shorter formula for 0, and this would be the formula, please bear with me, for e of 0. The formula is without the combination factors because it will always be equal to 1. So it will just be equal to d omega of 0 minus omega of 1 plus omega of 2 minus omega of 3, and plus so on and so forth alternatively. Okay? So this is the formula that may be used if what you're asked about is automatically how many of those elements are not having any of the given properties. We will have more illustration to this, especially examples where we don't have this table for us to really understand it in a more abstract level. Thank you very much for watching.